Hello. In this video, we're going to learn about symmetric matrices and diagonalization. In general, in the past, given a matrix A, for example, the 2 by 2 matrix A, B, C, D, we've learned that sometimes we can diagonalize a matrix. That is, to write it in the form P times D times P inverse, where P is a matrix containing eigenvectors of A as columns, and D is a diagonal matrix containing eigenvalues of the matrix A. Now it turns out, if instead the matrix A is a special kind of matrix we'll define later called a symmetric matrix, for example, a symmetric matrix could be of this form, A, B, B, D, then the diagonalization has some special properties. Right? If you write it in the form A equals P times D times P inverse, we're going to be able to say a lot of extra things about the matrix P. But before we begin, there's some definitions we'd like to talk about. First is something called the transpose of a matrix. So let's say you're given an M by N matrix called A. And remember, M by N, M is the number of rows, and N is the number of columns. The transpose of the matrix A, transpose of A, is an N by M matrix obtained by switching the rows and the columns of A. Obtained by switching the rows and columns of A. So in other words, it's almost like kind of turning the matrix on its side and switching some things around. So for example, let's do a few examples. If you have the matrix A, which is the matrix 1, 2, 3, 4, the transpose, since A is a 2 by 2 matrix, the transpose would also be a 2 by 2 matrix, but we would switch the rows for the columns. So if this is A, the transpose of A, which is often written with a superscript T, would be the matrix 1, 3, 2, 4. And as you'll notice, the columns of the matrix A, the rows of the matrix A, 1, 2 is the first row, corresponds to the column of the matrix A transpose. For a slightly larger example, let's say we had the matrix B. Let's say this is a 2 by 3 matrix. So this is the 2 by 3 matrix, 1, 2, 3, 4, 5, 6. So this is 2 rows, 3 columns. The transpose of B, written like so, would be a 3 by 2 matrix. So 1, 2, 3 down the first column, and 4, 5, 6 by the second column. And finally, even if you have something like a vector, you can think of a vector as an n by 1 matrix. So for example, if you had the vector 7, 8, you could consider the transpose of this vector. And this vector is a 2 by 1 matrix. So you could write the vector transpose as 7, 8, like so. That's a 1 by 2 matrix. And a few things we should observe about the transpose. So let's talk about a few notes regarding transposes. The first is if you take a matrix, you calculate its transpose, and then you calculate its transpose again, you get the original matrix. It's as if you had swapped out the rows for the columns and then switched the columns back into the rows. So if you take the transpose twice, you're left with the original matrix. This is kind of similar to something we've seen before. If you have the inverse of a matrix and then calculate the inverse of an inverse, inverting something twice returns you to the original matrix. In addition, if you have the identity matrix and you calculate its transpose, well, the rows and the columns are identical. The transpose of the identity matrix is also the identity. In general, this isn't true. Usually transposing turns something into a new matrix. But if A transpose does not change the matrix, if A transpose is equal to A, then A is called a symmetric matrix. It's a symmetric matrix. Right, so for example, if I have the matrix 1, 2, 2, 3, right, A transpose, right, if I turn each row into a column, you get 1, 2, 2, 3. Right, it's almost like it has a nice line of symmetry down the side, down the diagonal. All right, we should say a few more observations about transpose before we continue. So another thing I'd like you to take note of involves the dot product and the relationship of dot products to transpose. So let's say we have two vectors, call them v and w. Let's say v is the vector v1, v2, and w is the vector w1, w2. And if you calculate the dot product of these two vectors, we get v1 times w1 plus v2 times w2. However, right, the dot product is a special operation. If you were to just write these two vectors next to each other, right, v1, v2, and w1, w2, as if you're trying to multiply matrices, this is undefined. Because we have a 2 by 1 matrix on the left times a 2 by 1 matrix on the right, and the dimensions aren't compatible. Right? The number of columns of the first matrix should equal the number of rows of the second matrix, and that is not the case. So this is undefined. This doesn't make sense. However, if we were to take the first vector and calculate its transpose, and so if we do v transpose times w, multiplying as matrices, this is in fact well defined, right? Because v transpose would be v1, v2, and then the vector w is w1, w2, arranged like so. And here we have a 1 by 2 matrix times a 2 by 1 matrix. Right? The inner dimensions are compatible, so the result will be technically a 1 by 1 matrix. This would be w1 or v1 times w1 plus v2 times w2. And in general, when we have a 1 by 1 matrix, we'll just drop the bars on the side. And so we can just ignore those. And what do you know? This is actually exactly the dot product. Finally, one more note that I'd like to make. What happens if you do a transpose of a matrix times a vector? And so for example, let's say you have a matrix A times a vector V. The matrix A is A, B, C, D, and the vector V is X, Y. We've calculated this many times. As a result, you get the vector AX plus BY as the top entry and CX plus DY as the lower entry. If we were to calculate the transpose of this, right, the transpose of the product Right? Transpose means we interchange the rows and the columns. So we would get the 1 by 2 matrix, whose first entry is ax plus by, whose second entry is cx plus dy. Now, the question is, can we somehow distribute the transpose through this product, through A and V? And so notice what we get here when we do the transpose of the quantity, A times V, we get a 1 by 2 matrix. Now, if we want to write this in terms of the original A and the original V somehow, right, we're going to have to somehow have a result that is 1 by 2. The only way this is going to be possible, we'll have to multiply a 1 by something matrix. And so that leads us to maybe the transpose of the vector V times, right, you might guess that this is going to be V transpose perhaps times A. But if we try that, the numbers won't work out correctly. What we're really looking for here is V transpose times A transpose. Right? The reason being, think about what we need to do when we calculate A times V. Right? We take the matrix A, that comes first, we partition it into rows. If we're switching the A into the second position, right, we want the X and the Y to pair off with the A and the B, we're going to have to make those columns in this new calculation. So V transpose A transpose, when you multiply those through, you're going to get, well, precisely the same thing. AX plus BY as the first entry, and CX plus DY as the second entry. Right, so if you want to think of it as distribute the transpose operator through the product A times V, well, you distribute it to each one of those terms. However, you also have to reverse the order for the calculation to make sense. All right, so those are some observations on something called the transpose. And what we're going to be very interested in are symmetric matrices. Those matrices such that when you take the transpose, you don't change it. So the next main point I'd like to talk about involves symmetric matrices. Right, so if A is a symmetric matrix, right, and in particular, recall that means A is equal to its own transpose. If you swap the rows and columns, you get the same thing. And if it's also true that A has eigenvalues, say eigenvalues, maybe I'll call them, I'm going to really work with just 2 by 2 matrices here, has eigenvalues lambda and kappa with associated eigenvectors, maybe call them V and W, and if these are not the same eigenvalue, and lambda is not equal to K, then it turns out that the eigenvectors are perpendicular to each other. Or equivalently, the dot product of the eigenvectors is 0. And recall this also means that V is perpendicular to W. Right, so if we have something special about our matrix, that special property is somehow being reflected in the eigenvectors themselves. To explain why this is true, we're just going to use some properties of the dot product and some of the notes and observations we just made about the transpose. Right. To explain why, let's start off with lambda, I'll just pick lambda at random, times the dot product of V and W. Now, because of the way the dot product is defined, this is equivalent to saying, you can distribute this through to one of the vectors. And lambda times V is equal to A times V. Remember that the special thing about lambda, and also we'll see kappa, is that they're eigenvalues and eigenvectors. Right? So we know that A times the vector V is equal to lambda times the vector V. And similarly, A times the vector W is equal to kappa times the vector W. So we can replace lambda times V with A times V. Right? Dot product with W. Now, the next thing I'd like to draw your attention to, we recently made an observation that dot products can also be rewritten as transposes. Right? So we could write this as, we've got the first dot the second. We could write this as the transpose of the first, A times V, times, as in matrix multiplication, times W. We also made a note that we can distribute the transpose over a matrix vector product, provided we swap the order. As this becomes V transpose A transpose times W. And again, using one of our observations. Next is the part where we use the hypothesis that A is symmetric. And so A is equal to A transpose. So returning to my string of equalities, I can write V transpose times A times vector W. And again, that's because A is symmetric. It's a very important assumption. All right. Now, once again, I'd like to put some parentheses in here, and I'd like to think of this second part as a unit. Right? This is associative, so I'm going to group parentheses in this way. And once again, I find myself with a transpose times something. I can rewrite that as a dot product. So I can rewrite that as V times AW. Right? If I have first transpose second, I can write that as first dot second. So here I have a dot product. Now I'm going to again use the fact that I have eigenvectors and eigenvalues here. A times W, I know I can write that as kappa times W. So this becomes V dot kappa times W. But again, because of the way dot products work, I can take that constant kappa, and I can pull that out. I can factor that out to the front. So I'm left with K times vector V times vector W. So what do I have here? At the end, putting it all together, I have lambda times V dot W is equal to kappa times V dot W. However, lambda and kappa are not equal. Right? This is one of our original assumptions. Therefore, the only way this equation can be true is that V dot W must equal 0. Again, this is since lambda is not equal to kappa. Right, and again, if you have the dot product equals 0, equivalently, that means that those two vectors are perpendicular to each other. Excellent. So it turns out this is kind of a big deal. Right, to see why, now we're going to go ahead and talk about something which seems a little bit unrelated, but it's going to tie back in with what we were doing before. Switch colors again, because this is going to feel a little bit like a different thread in the conversation. So let's say that we're given some kind of a transformation, given a linear transformation right? Some kind of a function with a linearity properties. This is going to be f of the vector xy is equal to some matrix M times xy, where M is equal to, I'm going to write M with a kind of a focus on its columns, V1, V2, W1, W2. The columns, I'll refer to those as vectors V and W. So V equals V1, V2, vector W equals W1, W2. Let's say these vectors have some special properties. Let's say that the length of V, right, the double bar notation indicates length. Let's say that's a unit vector. Let's say the length of W is also equal to 1. It's also a unit vector. And V dot W, which is what we were talking about before, let's say V and W are perpendicular. Their dot product is 0. What kind of a linear transformation has these properties? Right, let's think about this for a moment. If we have this function and we plug in the first unit vector, or the kind of the standard basis vector actually, 1, 0, right, I get the vector V. If we plug in the vector 0, 1, we get the vector W. So this is a transformation which is going to send the basis vectors 1, 0, and 0, 1 to the vectors V and W. Let's go ahead and draw this as a picture. So I'll change some colors here. Let's draw a coordinate axis. I'm going to go ahead and draw a unit circle. What do we have here? We start off with the two basis vectors. Maybe I'll draw those in green. I don't think there's a lot of contrast there. Let's try a slightly darker color. Let's draw that in a dark blue. So I've got the vector, I'll call it I, right, one of the basis unit vectors. And let's say that it gets sent to the vector V. And if this blue circle is the unit circle, I know I can graph that vector V. So it starts at the origin. And it also coincides with a unit circle V. And again, because we're only talking about unit vectors here, the length of V is equal to 1. And I, basis vector 1, 0. And so all these vectors are placed as seen here on the unit circle. Also, we have the basis vector 0, 1, which I can write as maybe a slightly different color. Maybe I'll use black for this one. So up here, I have the unit vector j, which is 0, 1. And then that vector j gets sent to the vector w. Now, one thing we know about v and w, right, we know their dot product is 0, so v is perpendicular to w. That means on this diagram, I can draw the vector w like so. There is another possibility. It could be pointing in the opposite direction going this way. But for now, let's assume it's in this direction. Now, one of the cool things we have here is v and w are perpendicular to each other. Let me draw a little perpendicular mark. So what can I conclude about, any of these angles here? I can actually say a few things. In particular, since I and J are perpendicular to each other, and also V and W are perpendicular to each other, the angle, we'll call that theta, the angle between I and V must be the same as the angle between J and W. Let that sink in there for a minute. It moves or it rotates both these vectors by the same amount. Why must this be true? Well, let's think about it this way. Let's say the vector or the angle between I and V was alpha, and the angle between W and J was beta. Right, so given those two angles, and let's say the angle between V and J, let's call that something else. Maybe let's call that delta. Right, we know that alpha plus delta must be 90 degrees. Also, beta plus delta must be 90 degrees. So doing some algebra tells us that alpha must equal beta. And since alpha plus delta is 90, and angle beta plus delta is equal to 90, the only way that can work is if alpha equals beta. In other words, these vectors are being rotated by the same amount. So what kind of a matrix can do that while keeping everything on the unit circle? It turns out that the matrix M is a rotation matrix. Right, so we've learned previously that a 2x2 rotation matrix can be written in this form. Right, if you're rotating around the origin by theta, right, that's captured by this particular matrix. And so again, any matrix, right, whose columns have these three properties, right, both the columns have unit length and their dot product is 0, turns out to be a rotation matrix. And sometimes, these conditions are create what is called an orthonormal matrix. Right, ortho, short for orthogonal, which is another way of expressing the perpendicular condition, and normal, meaning normalized or unit length, is a way of explaining that condition again. All right, so any linear transformation with these properties must be a rotation matrix. Excellent. Now, what does this have to do with what we were talking about before? Well, if we go back a slide, right, a symmetric matrix, right, we might have something like this. So let's go ahead and let's talk about diagonalization. Specifically, as the title of the video indicated, we are interested in diagonalization of a symmetric matrix. Now recall that diagonalization involves writing a matrix A in the form P times D times P inverse, where we have eigenvalues, let's say lambda and kappa, and eigenvectors associated to these, let's call them V and W. In this case, P is the matrix with eigenvectors as its columns, and D is a diagonal matrix. Along the diagonal has the eigenvalues. And then you can calculate P inverse using a standard 2x2 inverse formula. All right, if A is symmetric, then we know that the eigenvectors must be perpendicular. Right? And that's one of the conditions we were just speaking about on the previous slide. But there's one question you might be wondering, how would we know if the eigenvectors have length 1? Do we know? If the length of this is 1, the length of V is 1, or the length of W is equal to 1? Right? Maybe it is, maybe it isn't. Do we actually have control over that? And the happy answer is that truly we do. Right? Recall that if we have an eigenvector, eigenvectors and eigenvalues satisfy the following equation. Right? A times vector V equals lambda times vector V. And remember the way that matrix multiplication works with constants. I can multiply both sides by some constant C. So C times AV is equal to C times lambda V. And because of the properties of matrix multiplication, right, I can go ahead and I can rearrange these as follows. A times C times V is equal to lambda times C times V as well. In other words, C times V is also an eigenvector. In other words, any multiple of an eigenvector is also an eigenvector. There's another way to think about this as well. When we're solving for eigenvectors, remember we had a free variable, right? And we could put in any number that we wanted there. So also, let's recall when solving for eigenvectors, right? We would always have a redundant system of equations, right? We'd be left with something like, oh, I don't know, 3 times V1 plus 3 times V2 equals 0, and maybe V1 plus V2 equals 0. And so, for example, we'd often end up with a system of equations like this, and we have a free variable. Right? So we'd often pick the simplest numbers that we can get to work. So we could pick V1 is equal to 1, in which case V2 is equal to -1, which gives us the eigenvector 1, -1. But we were free to choose any value for that first number, V1. Right? If we picked V1 is equal to, oh, I don't know, the number C, and we solved for V2 in terms of V1, that would have to be equal to -C. That would give us the eigenvector C -C, which is really just a multiple of our initial choice. And so any multiple of our eigenvector would also work. So how does that help us with, do we know if the two eigenvectors have length 1? The takeaway here is we can actually force them to have length 1. We can take an eigenvector and then we can scale it down or scale it up. We can divide it out by its length, and the result is still an eigenvector, but again, we can force it to have length 1. And if we do that, and so if we say the eigenvectors, and so this is the key takeaway here, if the eigenvectors have length 1, then the rotation I just spilled the beans. Then the eigenvector matrix is a rotation matrix. Right? Because we already know that the dot product of the eigenvectors is 0. They're both perpendicular, and they both have length 1. And that tells us a lot about how we can think about the matrix A. We can think of it as a combination of rotating and scaling in two directions, and then unrotating, rotating in the opposite direction. All right, so that's the idea. So what we'd like to do now is maybe do an example. We'll diagonalize some symmetric matrices, and then we'll figure out what rotation matrix we get from the eigenvector part of the diagonalization. That is quite the sentence. Let's work this out as an example. So for this example, let's try the matrix A equals 3, 2, 2, and 3. Right? A is symmetric. So we'd like to, first let's take note of that. We'd like to find the diagonalization where P is a rotation matrix. And so we're going to want an orthonormal matrix. We want both the eigenvectors, both the columns of P to have length 1, and because A is symmetric, they will automatically be perpendicular to each other. All right, so let's begin by finding the eigenvalues and eigenvectors as we normally would. We'll calculate the determinant of A minus lambda times I. And so that's the determinant of 3 minus lambda, 2, 2, 3 minus lambda. See, that's quantity 3 minus lambda times 3 minus lambda minus 2 times 2. So that works out to be 9 minus 3 lambda minus another 3 lambda plus lambda squared plus 4. This becomes lambda squared minus 6 lambda. Let's see, I have a 9 plus 4, which is 13. Actually, no, not 9 plus 4, excuse me. That wouldn't work out at all. I've got a 9. This should actually be a minus 4. Much better. 9 minus 4 is 5. There's our polynomial. We'll set it equal to 0. It factors quite nicely as lambda times 1, or lambda minus 1 times lambda minus 5 equals 0, which gives us our two eigenvalues, 1 and 5. Next, we'll find the eigenvalues. And so, as always, we have to solve A minus lambda I times the vector V is equal to the 0 vector. All right, so for this particular matrix, let's see, first we'll do the case where lambda equals 1. So we'll have 3 minus 1, 2, 2, and 3 minus 1 times the vector v1, v2 is equal to the 0 vector. Right, this turns into a nice system of equations. 2v1 plus 2v2 equals 0, and 2v1 plus 2v2 equals 0. So the easy solution is v1 equals 1, v2 equals 1, and that gives us the eigenvector of 1, 1. However, we would really like an eigenvector whose length is 1. So what we'll do is we'll turn this into a unit vector by dividing out by its length. Right, the length of this vector is the square root of the sum of the squares of the components. In this case, it's square root 2. So our original vector is a little longer than a unit vector. I'm going to go ahead and multiply this to get our new eigenvector. I'm going to divide out by its length. And so the eigenvector I would actually like to use here is 1 over rad 2, 1 over rad 2. And that's going to be the first column of our matrix P. Let's go ahead and find the second column as well. The second column will be for the eigenvalue 5. I'll call this one kappa just to keep it separate. So that'll be 5. And this time we're trying to solve A minus kappa times I times the eigenvector W is equal to the 0 vector. In this case, we have the matrix 3 minus 5, 2, 2, and 3 minus 5 times the vector W1, W2 is equal to the 0 vector. And turning this into a system of equations, we get negative 2 times W1 plus 2 times W2 equals 0. We get 2 times W1 minus 2 times W2 equals 0. And sure enough, we can solve this with W1 is equal to 1, W2 also equal to 1, which should give us an eigenvector of 1, 1. But again, this eigenvector does not have unit length. The length of this eigenvector is the square root of 2. And before, if we looked at these values, oh, you know what? Looking back at these values, I think I dropped a negative sign. I bet some of you watching caught that. When I calculated V1 and V2 to make these equations true, right, I really need to make one of these values negative. Right, this just occurred to me because I know I shouldn't get the same eigenvector twice. I should get 2 different eigenvectors. That V2 should make that a negative 1. Put a negative 1 in here for my eigenvector V. The length of V is still 2. That's still fine. But this first entry should be a negative 1 over radical 2. All right, much better. Going back to this page, right, the same calculation as before. I'd like to make W a unit vector, so I will divide out by its length. And for W, we will get 1 over radical 2, 1 over radical 2. So the diagonalization right, of the matrix A was matrix 3, 2, 2, 3 is equal to A. We wanted to write that in the form P times D times P inverse. We know what P is going to be. P is the eigenvector matrix. So that'll be first V, 1 over rad 2, negative 1 over rad 2, 1 over rad 2, 1 over rad 2, times the diagonal matrix, which has the eigenvalues in the same order, times P inverse. And what we'll notice here is it turns out that this is in fact a rotation matrix. Right, so in particular, rotation by what amount? Well, recall that rotation matrices rotation matrices have the form cosine theta, sine theta, negative sine theta, and cosine theta. And so we'd really like to solve for theta here. So let's say cosine theta, looking at this top left entry, cosine theta equals 1 over radical 2, also known as rad 2 over 2. Now, what angle has this as its rotation? Sure enough, theta is going to be 45 degrees, or pi over 4 radians if you prefer. One thing those of you might notice is that some of the signs in this matrix do appear to be a little bit off. Like for instance, you might know that the sine of 45 degrees is also rad 2 over 2, or equivalently 1 over radical 2. However, did you notice we have a negative here? But the negative appears to be in the wrong position. Why would this be? Well, the reason is, remember when we were trying to write down what the case is, and we drew a picture of the coordinate axes, right? And we drew ourselves a unit circle, and on this we drew the basis vector I, then we drew the first eigenvector v. We said that I is rotating into v, then we drew j, and then that vector w, we know that w and v are perpendicular to each other, so there's really two options, right? One of the options is one we drew up here. The other option for w is this. Right, so this is what's happening here. With these negative signs in the wrong position, that indicates that we also have a reflection in here as well. And so v and w are going in this order. So it's okay. It's still a rotation matrix, but it's a rotation matrix kind of combined with a reflection, which puts w on the opposite side that you might expect. Now, there's one final thing I'd like to talk about, which makes diagonalization of symmetric matrices really neat. And so we know that the matrix P is a rotation matrix. Cosine theta, negative sine theta, and cosine theta. But what happens when we calculate the inverse of this matrix? Right, if we do the formula for the inverse of a 2 by 2 matrix, we'll get 1 over the determinant. So we'll get cosine theta times cosine theta, cosine squared theta, minus a negative sine theta times sine theta. So that's sine squared theta. If you remember your trigonometric identities, you might remember that this is going to be equal to 1. The denominator is equal to 1, so the whole fraction's 1. And then if we change around the values in accordance with the inverse formula for a 2 by 2 matrix, we swap the cosine theta and the cosine theta, which appears to be basically no change. And then we negate the other two entries in the B and the C positions. And the interesting thing about this matrix is we can write this in a different way. P inverse happens to be the same as P transpose. Right? If I were to take the original matrix and divide it into rows, the rows of P correspond precisely to the columns of P inverse. And so this kind of matrix, an orthonormal matrix, is really quite special in that P inverse is also equal to P transpose. Just another fact we're going to want to file away. Next time, I hope to have a chance to talk about quadratic forms and how we can use some of this information in an application where we're going to try to graph conic sections. So putting it all together, we have that we can write our matrix A, our nice symmetric matrix A, with a diagonalization or a factorization like this. Now, as a parting thought, there's one question I'll leave you to think about. Maybe I'll write this in blue. What if you started off with just the knowledge that you could write A in the form P times D times P transpose, where D is a diagonal matrix? And so we don't necessarily pretend that we don't know that these have anything to do with eigenvectors or eigenvalues, but there's some matrix A that we can write where D has this form. Or maybe I should stay away from lowercase a and d. Maybe instead I'll just keep writing in this notation. If we are given this fact, and we know that D is a diagonal matrix, then what can you say about A transpose? And as a hint, A transpose should be the same as P times D times P transpose transpose. And think about what we said earlier in this video about a transpose of a product, and see if this simplifies and condenses to something else. All right, thank you for listening.